Okay, so let me first give you the motivation before I get into this Gibbsian business of tessellations. The motivations comes from the fact that the PDE, Hamilton-Jacobi PDE, T equals H X T UX is a very popular model for stochastic growth models, in the sense that if you regard U as a function that is from RD times, let's say, some time interval into R, and if you plot this guy, let's say this is RD and this is R, then this is U, this is your X. Then at time T, you kind of have some interface, maybe with some facets or something. And this represents an interface separated in different phases. And we're very much interested in the behavior, the scaling behavior of this function. And as is the common practice in the statistical mechanics, you often assume H is random. So this is a question of interest. You want to do a scaling limit for this guy. This is known as homogenization. And in the discrete version of this is known as hydrodynamic limit. They're all the same. And you want to go beyond that. You want to do central limit theorem. You want to do fluctuations. And we succeeded in proving some of these results only for a limited number of examples. And those limited number of examples are when some of these variables X, T, or U are discrete. And the reason that we succeeded in proving this, I shouldn't move so much. Oh, I forgot. The reason we succeeded in doing so has to do with the fact that some of those models are exactly solvable. You have very precise information about the law of the solution U, and prime example would be exclusion process or Hammerstein model. But we would like to go beyond exactly solvable models. And as the first step in this direction, we want to address the following questions. So this is a question of interest. Imagine that UX0 is distributed according to some measure mu0, and then UXT is distributed according to a measure mu-t, and find an evolution equation for mu-t, which is kind of like an evolution equation that has enough information that would allow you to address those questions. And of course, this is just too general to have a simple formula for the evolution of mu-t, but instead you can ask the following question. Is there a family of distributions, say M? So M would be a suitable family, which depends on this Hamiltonian function H. So is there a family of distributions that is invariant under the dynamics of this PDE? And that family consists of nice probability measures. And in the case that I'm going to describe, this family would consist of Gibbsian type measures, Gibbs-like measures in continuum. So there's a family of distribution that is invariant. With respect to evolution of the PDE. Okay, and oh, there's only one. Then what is this? Wow. Then what you're hiding it? Oh, because this is a board talk. Amazing. Okay. Maybe I hide it totally to kind of avoid confusion. Okay, so we've been able, in some works, we've been able to kind of answer this question positively. And the key word is that in dimension 1, when the family consists of Markov processes, and in higher dimension consists of Gibbs measures. So So we have some results when d equals 1, HXTP is convex in P, or D is positive, H is independent of P, but still convex, and the initial data is convex. Okay, so these are some of results that we so far we have for this problem. And in this case, this comes from several works that I've done with Dave Kasper. So the motivation, let me kind of give you a little bit about the case d equals 1. D equals 1, there was a conjecture of Menon and Srinivasan. So after there was a conjecture of Menon Srinivasan that goes like this, that if at time t equals 0, you have a picture like this, the initial data looks like this and is Markov, meaning that you have all these deterministic pieces kind of satisfy some ODE. It's like have a Markov jump process plus a drift.
Which data you use UX0?
That's right, t equals 0. This is UX0. If UX0 looks like this, it's piecewise smooth with Markovian jumps. And so there is a jump kernel that if this is rho minus and this is rho plus, the jump happens with rate f of rho minus rho plus 0. So if you have a picture like this initially, then this picture persists at later times. So at t equals 0, same thing, but now the rate changes to this guy. And more importantly, you have a very precise distribution for the evolution, for the description of the evolution of this guy as a function of time, this kernel. This kernel satisfies some kind of kinetic type equation. And F solves a kinetic equation, which looks like Ft equals a suitable quadratic function Q of F. This is quadratic. I give precise description later when I go to higher dimension, but for now, you have such a closure description. Yes?
When you say solution, you mean viscosity solution for the...
That's right, viscosity solution.
But then the discontinuities are the ones that satisfy the...
viscosity solution. Otherwise, this is not true. I start with a profile that looks like this and evolve it according to Hamilton-Jacobi equation, but assuming the solution is a viscosity solution. And then I'm saying that you lose information. That's the point here. If you start with the profile initially, you go for later time, you do lose information. Nonetheless, it's going to be a Markov process, and you have a very precise description for the Markovian kernel. And this thing is a kinetic equation. And I mean, this meeting is for particle systems. It turns out that the location of these shock discontinuities can be treated as collection of particles. And then you figure out what the dynamics of these particles are. These are particles with velocities, and when they meet, they merge to kind of form another particle. And that's why the description is given by a kinetic-like equation. Yeah, makes sense? So this is their conjecture. And this conjecture was established. So I think the conjecture was formulated in maybe 2010, if I remember correctly, or 2012. And then I worked out on this conjecture, and with Dave Kasper and myself, we established this conjecture in 2 papers. I think it's about 2016 and 19. And in the first paper, to establish this, we considered a much simpler situation when instead of having a picture like this, imagine this piece is trivial, namely is a flat profile. So the case that we treated in 2016 looked like this. So initially you start with a picture that looks like this. And this picture persists at later times. Then there is a jump kernel here. So you go flat and then make a stochastic jumps and go flat. And then again, you have a situation like this, and we managed to establish that. So that's the picture that you have in dimension 1. And then later, I also managed to extend this to the case when H can depend on X and T. You know, this picture, but with H depending on X and T. So there's this FR 2000, I don't know, maybe I finish it this year, maybe 2, but who knows? And life is so tough. God knows what comes in your way. It may never happen with COVID. Now, the focus of today's talk would be higher dimension. So today's talk. D bigger than 1. And you know, I want to kind of, the case that I can treat it would be the case when you have this picture to in higher dimension. So let's understand the meaning of that picture. You see that this, by the way, this is not U, this is UX. This is UX. I apologize. This is the derivative of U. Okay. So D bigger than 1, I want to have a situation over there in the first work that I mentioned. You had the situation when UX rho, the derivative of U, is piecewise constant and is increasing. In terms of U, that would be when U is piecewise linear convex function in dimension 1. The generalization of this to higher dimension would be when UX0 is piecewise linear convex function. The point is that the family of piecewise linear convex function, it's invariant under the flow of the Hamilton-Jacobi equation, provided Hamiltonian does not depend on X and T. So the fact is that if UT equals HUX with H convex, then at later time, UXT is also piecewise linear convex. Okay, so that's the easiest scenario to study as a warm-up. And one should be able to extend it to the case when this is kind of more complicated, and this H also depends on X and T, but that would be future work. But for now, the easiest scenario is that H is independent of XT, H is convex, the initial data is piecewise linear convex, and at later time you have the same type of profile, and you want to describe the evolution of such a profile. So that's the goal. Okay. So the claim, I want to choose initially this guy stochastically according to some Gibbs-like measure, whatever it means. The picture persists at the time. This is going to be also Gibbs-like measure. And guess what? I'm going to kind of like mimic the same situation. Previously, the derivative of U, rho, was experiencing all these stochastic jumps in a Markovian fashion. And the jump was described by a kernel. I want to start with a kernel, use that kernel to figure out what that Gibbs measure is doing initially, evolve with time, and then hopefully derive a kinetic-like equation for the evolution of the kernel. So that's the goal. So there would be 2 steps. Step 1, we build a family of Gibbs-like measures for the law of rho equals UX that is invariant. under the dynamics. And step 2, we derive a kinetic equation for such measures. And this is the joint work with my current student, Mehdi Waki. So this is Mehdi Waki. So there are 2 parts into it. First, you have to come up with the right notion of Gibbs measure in this setting. What does it mean? And once you figure that out, then the second step would be showing that indeed this is invariant under the dynamics and derive an evolution equation for the kernel. Kernel is the analog of potential, the log of that kernel. Is the analog of potential when you study Gibbs measures in some sense. Okay, so task 1, build. So this has nothing to do, this part has nothing to do with the Hamilton-Jacobi equation. We can forget about Hamilton-Jacobi equation for now and just think of building a probability measure on the space of piecewise linear convex functions that has a little bit the flavor of a Gibbs measure. Okay, so build a probability measure on the set of sets, let's say C for convex of piecewise linear convex. Given, so somehow what I have in mind is that I want to build that probability measure so that it's invariant under dynamics. So of course you should keep that in mind. But somehow I want to kind of mimic that scenario. So it's going to depend, the measure depends on one kernel. That's the analog of potential. Given a kernel, which I denoted by fx rho minus rho plus. Okay, I think now we've reached the equilibrium state here. Where here, and let's say we do it in dimension 2. And you know, the construction is somehow suggests that there is a possibility to extend it to any dimension. Because in fact, the idea is that some of the ideas in dimension 1 is used to build the problem in dimension 2. Then you can kind of mimic that and from dimension 2 build something dimension 3, so on and so forth. So there's some kind of induction going on here, but for now, let me assume the dimension is 2. So, and this kernel is a function of x, which is in R2, rho minus, which is in R2, and rho plus in R2. And the way to think about it, f of x rho minus rho plus in some sense represents the rate at which you, at position x, you jump from the vector rho minus to rho plus. And don't forget, rho is the derivative of ux. This is a vector. So that's the, intuitively, that's what's going on. And before, it turns out that for such piecewise linear convex function, what comes into the game is some geometric combinatorics. So, so let me explain that. The first observation, I claim that there is a 1-1 correspondence between the space of piecewise linear convex functions and the set of the so-called Laguerre tessellations. I claim that, in fact, what you are dealing with is just a suitable decorated tessellation of the plane. So let me explain that. So I have a hard time to draw a piecewise linear convex function, but you know, basically, if this is your R2 and this is your rho, which is ux. Okay, so let me start with u for now. If this is your function u, so this is a piecewise linear convex function, there would be all these facets. And if you kind of look at one of the facets of the graph, you know, it would kind of maybe it looks like this. And when you project it down here, it turns out the convexity would force to have a polygon here. Oh, there are more edges. So when you project it down here, you would have a polygon. So, you know, the function is piecewise linear, which means this has a suitable slope. The slope would be a vector. So take that slope. So let's say the slope of this guy is rho. In other words, your u down over here would be a function which is x dot rho plus a suitable constant, call it. In fact, that would be the Legendre transform of this guy. So let's say the constant c that depends on this guy. And then you project it down here, the set on which the function u coincides with this linear function would be a suitable polygon, though you have to remember that the other piece of information that is relevant is the slope of this guy. So not only you have a polygon, associated with this polygon, you have a vector rho. So when you put pieces together, when you look at down here, what you see a kind of polygonal tessellation of R2, and each cell of this tessellation is weighted or decorated by a vector, and the vector are exactly the slopes of your functions. So the kind of picture that you can think of down here, so this is now your R2, maybe would look like this. Make it kind of more natural. So you get a tessellations. They're all polygonal convex polygons, and each one is kind of decorated by a vector. So that's the situation you have now. So it boils down. Yes.
Sorry. So the constant won't matter.
Because you see, actually, I'm going to build the probability measure for rows, not u, for the same reason that I built the probability measure, that Markov jump process for the derivative. So the constant would not matter. So you, right, the constant would not matter. That's right, for this description. So now if you give me a tessellations that are decorated, you have to make sure that the decorations would allow me to build u out of that. After all, this function rho is an exact derivative, is the derivative of scalar value of function u that is convex. So you need to put some conditions to guarantee that. It turns out that if you look at two adjacent cells that are decorated by rho minus and rho plus, to guarantee that this decorated tessellation is an exact derivative, or the corresponding function rho is the derivative of scalar value of functions, you need a condition relating the slope of the edge separating rho minus from rho plus to rho minus and rho plus. It turns out that if the vector that represents the edge is tau, then the condition is tau dotted with, in fact, tau should be orthogonal to rho plus and rho minus. So if you make that assumptions, then for sure, the function associated with this decorated tessellation comes from the derivative of scalar value of functions. But how do you know that function is convex? It turns out that, you see, if you look at this vector pointing from rho minus to rho plus, draw that vector is orthogonal to tau. And not only that, the direction of that vector should be from the rho minus side to the rho plus side. If you make that assumptions, if you have that property, then for sure this comes from a convex function. So because of that, then I can forget about the convex function altogether and just focus on the space of tessellations that are decorated with this additional condition and the fact that rho plus minus rho minus, when you draw the vector, this is the vector rho plus minus rho minus, is pointing from rho minus side to the rho plus side. Yes.
So
a very silly question. So tau is two-dimensional, but rho plus minus rho minus is three-dimensional.
Right. In higher dimension, you have an kind of a face which is of codimension 1.
Okay.
So it's orthogonal to that face and is pointing from one side of the. You see, the cell now is, let's say you're in dimension 3, is a three-dimensional thing, and the boundary of such a cell would be now two-dimensional, guys. So rho minus rho plus would be orthogonal to that plane, and it has to point from rho minus side to the rho plus side. So yeah, it makes sense in any dimension. Yes.
I don't think I figured this quite properly. In dimension 1, for example, could you make the same? Would it be easier to illustrate it like?
Right. In dimension 1, rho plus rho minus is in one direction.
Okay.
And has to do, right. So let's say this is rho minus, this is rho plus. Okay, the tessellation in dimension 1 would be just a bunch of intervals. And you're just going rho plus minus rho minus would go in the positive direction of x-axis. And indeed, it's from rho minus side to the rho plus side. So, I mean, the kind of picture you have would be rho minus is here, rho plus is here. Since rho plus is strictly bigger than rho minus because I have an increasing function, rho plus minus rho minus is a vector that is pointing in the positive direction, which is indeed pointing from rho minus side to the rho plus side. Okay, so that's the analog of monotonicity that I had in increasing function is the analog of that. Yeah, very happy. Stefano doesn't look happy, you know. I know you for how many years? I can easily tell what's happening in your mind. I mean, you're smiling, but I know you're not happy. Okay. All right. So here you are. I want to kind of build a probability measure on this set of tessellations. How do I do that? And you know, something interesting happens. Now the question is what the dynamics is. When you evolve this according to Hamilton-Jacobi equation, then these tessellations are going to evolve. And one can figure out exactly what the dynamics are. Actually, these edges start to move with the dynamics, but they move without, the angles never change. So they move in the sense that you have the same picture, the same angles, but it may kind of, some of the edge can move back and forth. And it turns out, I can kind of tell you exactly what the dynamics is. It turns out that when you have a triangle, the triangle can only shrink. And once in a while, one of the triangles shrinks to a point. So once in a while, you lose a face. But otherwise, that's the only way that you lose a face. So one can kind of describe the dynamics very exactly. But that comes later. For now, I just want to build a probability measure on this set of all possible tessellations. So now they measure. Using f. So this is the only information I have. You give me a kernel, f of x rho minus rho plus. I want to give you a way of building this measure. So, well, I mean, the natural thing is that you want to do it like a Gibbs measure. I want to build this measure for tessellations in the plane. First, I build it on some bounded domains, maybe like this. That better be convex because everybody here is convex. I build the measure here, which means the intersection of tessellations inside this guy. And that's the result of doing everything by hands. So like there's a tessellation inside here, and then I make the domain larger and larger. And if I do it right, these measures are consistent with each other, and I have a probability measure there. Again, what I have in mind, I have to give you a candidate that is invariant under the dynamics of Hamilton-Jacobi equation. So you should keep that in mind. But how you do that? Well, it's kind of pretty tough to do this. I mean, if you have a Gibbs measure, how do you do that? You give me a boundary condition for your domain. So the boundary spins or whatever you want to call it are assigned. And then you give me a potential that says how you use that boundary condition and build the configuration inside the domain. That's the general strategy. I want to kind of follow the same strategy. And the way I do it is that I look at my tessellations that I would like to build. I look at the intersection of the tessellation with the boundary. The intersection of the tessellation with the boundary indeed gives a one-dimensional tessellation on the boundary curve, whatever it is. And that one-dimensional guy, I already have a candidate for it. Maybe I do it in a Markovian fashion. I do it on a Markovian fashion on the boundary, and then use my potential that is associated with F and build things from that information inside. So that would be the general strategy. But how do you carry that out? Well, let's just solve a simple situation. Suppose I want to kind of build the tessellation. I don't know what's happening inside. First, I want to build the tessellation inside the domain. And I want to do that in a Markovian fashion. Of course, you have to be careful because this is a closed domain. If you build a Markov thing, you have to condition that when you come back to where you started, you end up at the same place. But let's do it in a naive way. And suppose that according to my Markovian dynamics, I start from some point here. I tell you that the slope is rho 0. And then I move counterclockwise, and then some Markov Poissonian clock rings according to this kernel. Then it gives me another guy, which means that when you started from rho 0, then you have to switch to rho 1 here. So you started from rho 0, now you switch to rho 1. But if you know rho 0 and rho 1, these are two vectors. Because of this description, the edge that is emanating from this is the slope is determined. So there is a unique candidate for that edge. But the thing is, if you draw this edge and there would be no other Markovian points here, this edge is going to intersect the domain at another point. So not every point on the boundary can be kind of stimulated using these Markovian law. Some of them can be determined, not all of it. But how you would know which one to select? Well, what's happening is that, you see, there's this tau that is separating two faces. If I give an orientation to these taus in a suitable manner, then I can I have a direction on each edge. So I have a kind of direction here. Then I realize that if there is an orientation for the edges separating different cells, then these 2 points, one of them you can regard it as an entering point, the other one would be an exiting point. So when I build the configuration on the boundary, I try to only, for example, determine in a Markovian fashion the entering edges, not the exiting edges. And I let the exiting edges to be determined later. And that's the only thing I can, only a strategy I can think of. So somehow use your kernel fx rho minus rho plus to build the intersection of the tessellation with boundary for entering edges only. Let me be more precise. 5 minutes. Oh, 5 minutes, man. Okay, so so kind of to simplify the matter, I assume that the probability measure that I'm building, this Gibbsian measure that I'm building, all edges are pointing upward and to the left for simplicity. Otherwise, if you assume that, then the convex set that I'm kind of building the configuration here can be chosen to be a box. If that is not the case, then you have to kind of tilt the box a little bit so that this always would be the case with respect to the domain. So, I want to kind of build your probability measure by building the smaller domains and make it larger and larger. If you want to choose it to be boxes, then this condition would be pretty helpful. Otherwise, you just change your domain a little bit. So let's not worry about that. Assume with probability 1, the edge is always pointing upward and to the left. If you make that assumptions, then you kind of do it in the following way. So there would be all these edges that are entering this way. So everybody on the top and the left would be exiting guys. So I just have to build the configuration on these boundaries. And I do that in a Markovian fashion. So if you're going first along this way, if you have rho minus, then when you go to the right, rho plus, you do that with rate f of rho minus If this is a point X, you do that fx rho minus rho plus. So just in a Markovian fashion, you start from this corner, go to the right with this kernel, make a jump once in a while, and make sure the support of this measure, you assume the support of the measure is such a way that the edge always pointing upward and to the left. And then do likewise on this guy. You start, when you reach this corner, then you make a turn, go up in a Markovian fashion, and do likewise, though the kernel should be changed a little bit. In fact, it's not f that would be the right thing to do. It would be tau dotted with n, the positive part, that is the right rate when n is the normal direction to the boundary and tau is the direction of the edge. You really have to do it in this fashion in order to do it successfully. So with this rate, make sure you build your configuration here. So you build your configuration. Now, out of that, you build the configuration inside. And what happens is that you start from the bottom. Once in a while, you may have an intersections. I mean, like this, for example. Okay. So you do that in a deterministic way. You start with the edges on the boundary, you move inside, and once in a while you have an intersection, and then there would be, let's say this is row 1, this is row 2, this is row 3. So before the intersection of edges, you go from row 1 to row 2, and then row 2 from row 3. Afterward will be from row 1 to row 3 only. So this much is deterministic, but that's not enough to build your Gibbs measures. Once in a while, you have to figure out when to branch off. And in order to build your measure successfully, the rate of the branching should be stochastically, and that should happen in a Markovian fashion. As you go, start from the bottom, go up, would be of the form f of, let's say you start with rho minus and rho plus, and you want to branch off and produce rho star here, would be at the point X, would be f of x rho minus and rho star, and f of x rho star rho plus, and then you divide that by f of rho minus rho plus. And here you see that you look at the slope of this, there would be a suitable velocity of these vectors that would be one associated with this and one associated with this. So there would be a suitable difference of the velocity or direction of these guys that you put here. And then you have to make sure that this rho star that shows up here would allow you to go away in this direction. So there would be some kind of like plus sign here. So this I'm not going to write it down because I don't have time, but with this rate, you build the probability measure. So there would be some kind of splitting here that you do it once in a while. But now the question is, as you enlarge the box, whether these measures are consistent. Now the claim is that they are consistent if and only if you look at tau times f and take the divergence of this with respect to x, this equals to a suitable qf, which is quadratic here. So in order for these measures to be consistent, f must satisfy a kinetic equation. And once this is true, then you can build your measure. And guess what? This measure you built is invariant under the Hamiltonian dynamics, Hamilton-Jacobi dynamics. And not only that, you start with an f that satisfies this equation, you take that f and then build another kinetic equation that would give you the kernel at later times. Okay, maybe it's a good time to stop.
Well, thank you very much. Questions?
How this measure depends on the original Hamiltonian, the Hamilton-Jacobi, or could be anything that you construct? No, because something must depend on the Hamiltonian.
No.
No.
These measures independent of the Hamiltonian. However, you start, so you give me your favorite f, any f that satisfies this equation. You know, the, right, there is no, you see, you give me rho minus and rho plus, then tau, the direction separating the edges is already determined. And that all matters because I have to build these edges or something. So this equation doesn't depend on Hamiltonian at all. So you give me a kernel that satisfies this kinetic equation. I can kind of write it down explicitly for you. You take that solution, that F that depends on x1 and x2, rho minus and rho plus. Then out of that, you built another kernel that depends on time. That new kernel satisfies a new Hamilton-Jacobi, a new kinetic equation. That new kinetic equation now depends on H because you want to satisfy the Hamilton-Jacobi PDE. And you see, if you want to relate this to that new equation, it would be the case. See, if you assume the support of this measure in such a way that rho minus and rho plus lies on a graph of a function, meaning rho plus is always k of rho minus. If you make that assumptions, then this QF now depends on your k. You see, this measure, I'm not giving you the details, but you can assume, for example, its support is a graph of a function. If you make that assumptions, then that function is your Hamiltonian function. So what happens is that the one you built for Hamilton-Jacobi PDE has the same flavor, but now you're building a kernel that lies on a graph of a function. And why that is relevant? Because if you satisfy this Hamilton-Jacobi equation, if you look at the slope and regard t as your third coordinates, then you see that one of the derivatives can be expressed as a function of the other derivatives, which means if you look at ut, ux1, ux2, x3 as a triplet, that indeed lies on a graph of a function.
So there is a question online. Thierry?
Yes, just a quick question, thank you. I was wondering, so the evolution will be dictated by this kinetic equation, which seems extremely singular because you have this branching and this coalescing particle. I mean, it seems even more singular than a Boltzmann equation.
And I explain why. Okay, so you see, here I'm giving a recipe for constructing the measure for tessellations in R2. So now I claim that the theorem I stated in the beginning, which was you have this piecewise monotone guy, you solve some kinetic equation, and then at later time you have piecewise monotone. I claim that indeed gives a candidate for this measure. The reason is this: suppose you're in dimension 1, and suppose ut is hux. Then when you draw a picture for the evolution of rho, so let's say this is x, this is t, then you see the function would be piecewise constant, and then you would have all these shocks that are interacting here.
Mm-hmm.
Okay. In other words, if you look at the pair ux and ut, then, and this is your vector rho, then you have a vector. Then you see in each cell in this picture, indeed, the function rho is constant. And then what you built here, even though you solve this differential equation, you can regard this as an example of a random tessellation when you take into account the time variable as well. Okay. So that's why here you have an example of a tessellation that has additional condition that this rho belongs to the graph of H. So that's the motivation. Even when you solve the problem in dimension 1, you can use that to build an example of a random tessellation in dimension 2. Now, this work says that you can do a similar thing, except that you can go beyond the graph of a function. In other words, I can build a tessellation that does not lie on a graph of any function. That's why these two things are similar.
Mm-hmm. Okay, thank you.
Well, we are over time, so I have to interrupt the discussion. Thank you very much, Fraydoun.